Yeah, in continuation to our continuous distribution, there is one more aspect called Poisson process. We have looked at Poisson distribution, which was a part of our discrete distribution. What was that Poisson distribution used for? We have primarily used it to model the number of claims or number of something in some unit of time, in one day or per 6 hours or whatever it is. So number of claims in 1 month, in number of claims in one day per unit of time. So whenever we are talking of modeling per unit of time, probably you can use the Poisson distribution. So there the time unit is constant. Whereas if I make the time unit variable, so which means in some time t, like I know that there are some kind I know that the number of claims per hour is 5. Then if I want to model the number of claims in 5 hours, what is the chance that there are not more than 10 claims in 5 hours? So for those kind where the t is a variable, I can model for half an hour. I can, though I know the information that per hour I get 5 claims, I can model for half an hour, I can model for 10 hours, I can model for 200 hours. So that is where we are calling that extension of the Poisson distribution, because Poisson distribution is more focused on per one unit of time. But that if that time itself can be made as a variable, we are calling it as a Poisson process. So we are saying the number of claims or any event in some time t, not per unit of time. So whenever we have a parameter called lambda for a Poisson distribution, that is per unit of time. What you can do is lambda t, you can make it as a parameter for your Poisson process. So that lambda can be either increased or decreased for your Poisson process. Like this, if you take this example like this, the number of deaths among the retired members of a pension scheme occurs at the rate of 5 per month. So the average rate is around 5 per month. So what I am saying, lambda is equal to 5 as per this Poisson distribution. Lambda is equal to 5. But he is saying calculate the probability of 18 deaths in 5 months. So here I need 5 months, right? So probably the lambda t which I am taking, I can directly take it as 25. 5 per month. So the average is 25 per 5 months. That is what I am taking as a Poisson process. Now he is asking me what is the probability of 18 deaths in 5-month period. So 18 deaths in 5-month period, I can very well work it out, because the probability of x equal to 18 as per the Poisson distribution is nothing but e power minus lambda x into x per lambda, lambda power x divided by x factorial. E power minus lambda x into lambda power x by x factorial. So you can very well substitute x equal to 18 and lambda you can substitute as 25, and you can solve this particular exercise. Right? E power minus lambda, no, there is no x here. The formula goes as e power minus lambda into lambda power x by x factorial. Using that, you can substitute x equal to 18, lambda equal to 25, and you can get your probability. What is the probability of? So the only difference is, instead of taking it for that one single period of time, we can make the time completely variable factor, and that is what we call as a Poisson process. And whenever we talk about the waiting time between the two occurrences, we use the exponential distribution. Even so, between two Poisson uh, when something is following a Poisson process or any Poisson distribution, the waiting time between the events, we can model them as a exponential distribution with that same lambda itself. For example, if the reported claims follow a Poisson process with the rate 6 per day, right? So the rate is 6 per day. So I'm directly taking lambda to be equal to 6. Calculate the probability that there will be fewer than 3 claims reported on a given day. So actually I have to find out probability of x equal to 0 plus probability of x equal to 1, a straightforward problem, a normal Poisson distribution problem. Probability of x equal to 2, fewer than 3 claims. So this becomes e power minus lambda into lambda power 0 by 0 factorial. Like this I can very well do e power minus lambda into lambda power 1 by 1 factorial. This is the way whatever we substitute, we get, because this is also per day and the question is also on per day. So there is nothing to adjust there. But now look at it like this. The time until the next reported claim is less than 2 hours. Right? We are getting this lambda is 6 per day. So probably you can either convert it into per hour, this you convert it into per hour, or this you convert it into days. So probably if I convert it into days, this becomes 1 by 12 days. 2 hours is 1 by 12 days. Right? And he is saying that the next reported claim, which means the waiting time is less than 2 hours. So I can model it as an exponential distribution. So I'll take it as 0 to 1 by 12, because anything between 0 and 1 by 12 hours only I want to find out. And for an exponential distribution, it is lambda into e power minus lambda x. So lambda is 6, e power minus 6x dx. So which is becoming 6 by minus 6 into e to the power of minus 6x, where we are doing it between 1 by 12 and 0. So this is anyhow minus 1. So this becomes e power minus 0.5 minus 1. So it is becoming 1 minus e power minus 0.5. Whatever is the probability that is associated with it, 1 minus e power minus 0.5 minus e power e power let me just use spreadsheet. That would be better. So what is it? 1 minus e power minus 0.5. 1 minus e power minus 0.5 is giving me around 0.39. So there is a 39% chance that the next claim would be in less than 2 hours. So a 61% chance that the next claim would be after 2 hours. Right? So that is the typical way we can look at if we are going with Poisson process. So it involves two things. One, the Poisson distribution to model your number of claims in some unit in some time period, and two, the waiting time between the claims can be modeled using the exponential kind of a distribution. Then one more aspect which is present in this is the random number generation. Because see, what happens is, if at all on a random basis, see, simulation is a world where I am trying to generate the data from the distribution. Generate a data from the distribution. Let's say I only know some characteristics of this data. Let's say the mean of this data is 0, variance of it is 1. But generate one value for it. Right? I don't have the raw data with me, but I have the parameters of that data. Probably it's like this. The average height of an Indian male is 165 centimeters. And the standard deviation is 5 centimeters. And it follows a normal distribution. Let's say only this information we have. We don't have the data with us. We have only this information. Now, using this, I may look at generating the data in the reverse way. Right? So, that is the process of simulation. Because, see, I would like to know, very simple. Let's say the question is like this. The average height of an Indian male is 165 with a standard deviation of 5, and it follows a normal distribution. Now my question is, what is the chance that any person selected at random will be less than 140 centimeters? Right? I don't have the data to say what is the probability that this person's height will be less than 140, right? I only have the information of this much. The mean is there, the variance is there, and the distribution is there. Based on that, what is expected is, because you know that it's a normal distribution, you can generate the graph and you can do everything out of it. Right? You know the mean, you know the variance. So you can generate the data. And how do I generate the data? That is what is being done using the concept of random numbers. What they simply do is, there are tools typically which are available, which will generate the random number for us between 0 and 1 in a completely random fashion, where it's like a uniform distribution. All the values have equal chance of getting generated. If I see in Excel, there is a formula called RAND. What it does is, it generates some number for me. It keeps on a random basis, that value keeps changing. Between 0 and 1, the value. So between 0 and 1, the value keeps changing. So now, here this is following a uniform distribution. All values have equal chance of occurring. We don't know what value is generated also. That is what we are calling as the random number. Right? Now, the point is that random number is following a uniform distribution, 0 to 1. How do I generate the equivalent of that to some other normal distribution, or a binomial distribution, or an exponential distribution? Because exponential distribution may not lie between 0 and 1. Binomial may not lie between 0 and 1. The values may be anything. Now, but the random number will generate only between 0 and 1. Now, using that random number, value generated between 0 and 1, how do I take the equivalent of that to a particular distribution is what is the random number simulation process. One similarity which we find is for any probability distribution, the total probabilities is always 1. The sum of all probabilities or the cumulative probability distribution is the maximum is 1, minimum is 0, right? So that concept will bind the random number generation process as well as the probability distribution process. Now for any curve, let's say here, whatever is the distribution for it, I am not bothered. Let's say this is my cumulative probability distribution curve. So obviously this is 1. Now let's say if I want to find out the value corresponding to 0.6, what I'll simply do is, I'll put 0.6 here, draw a line onto the curve here, draw a line onto the curve here. This will say this will be the value of x. So which means we are doing an reverse calculation on that formula. Reverse calculation on the probability cumulative distribution function. Random variable we are finding using a random number. We want to find the random variable. It's like this. You are right. Mean and standard deviation are available. I am trying to find out the variable itself. Like, okay, which of the 6 will come on the dice? Let's say if the random number is given as 0.222. Corresponding to this, what is the random variable which is associated with throwing of the dice? Right? So we are doing a reverse calculation, generating the number from the random number. We are because random number could be as random. It's like this. I want to pick up one value from a normal distribution. I know that the data is a normal distribution with a mean of this much, with a variance of this much. I want to pick up one value at random out of that group, right? So to create that randomness, what I am doing first is, randomly I am asking my system to generate a number between 0 and 1, where no human bias is involved. So that whatever is generated as 0 to 1, I am mapping it to the cumulative probability value. Based on the cumulative probability value, I am generating the random variable. So because we are doing an inverse work there, we call that as the inverse transformation method. The simple thing, probably you can, let's say we talk about this. Exponential distribution. So he is giving 3 random numbers for us. In the exam, he will give typically the random numbers, some number. Otherwise, they are using a system like as I was generating rand formula, will keep generating the random numbers for us. Now, what he generally asks in the exam is, okay, now if I am giving you these 3 random numbers, which are coming from a uniform distribution, because they come between 0 and 1 with equal probability. Now, you find the equivalents of these in the exponential distribution, which is having a lambda of 0.2, right? Which means first I require the cumulative, I require that cumulative distribution function, because that's where the cumulative distribution function will lie between 0 and 1, right? So for anything, I am taking the cumulative distribution function. So in this case, in the exponential distribution, cumulative distribution is nothing but the integral between 0 to x lambda e power minus lambda x, which is nothing but 1 minus e power minus lambda x. This is our cumulative distribution. Now what I can very well do, lambda is already known, 1 minus e power minus 0.2x. This is my cumulative distribution. Now because this will lie between 0 and 1 only, I will take one random variable and assign to it. So what is that? It is becoming 1 minus e power minus 0.2x is equal to 0.311. So from this what is coming out? E power minus 0.32x is 1 minus 0.311. So what it comes? Okay. 1 minus 0.311. This is e power minus 0.2x. If I take the logarithm of it, it becomes minus 0.2x. Minus 0.2x. This is minus 0.2x. So I take the minus, it becomes a 0.2x. So divide by 0.2 or divide this by minus 0.2, this becomes x. So it is saying my random variable is 1.86 corresponding to this. Corresponding to, so it is nothing but if I try to find the area from 0 to 1.86 which we got under this exponential distribution, the area will be 0.311. So we are actually doing a reverse work, which random value is any value generated between 0 and 1. We are mapping it to a probability value because probability value will lie between 0 and 1 for any distribution. So to generate the reverseness, what we are saying is we are equating whatever the number that is generated. This we are not bothered. These numbers are generated in a very random fashion. No algorithm, nothing associated with them. If you see, these keep changing. See, because it's like this. On a random basis, I want to pick up one value. I don't have data with me. See, it's like this. I am telling you that the average height is 165, the standard deviation is 5, normal distribution. Right? Generate 5 values that come from a normal distribution. The practical usage of that is generate 1000 values. Out of them, tell me how many of them will fall below 140 centimeters. See, because that information is not available with me. The only information that is available with me is the average and the standard deviation. So basically I am trying to, based on the exponential or normal distribution data that I am having, what I am doing is I am reversing it. I am equating a random, on a random basis I want a number to be generated. And because the probability, cumulative probability is equal to 1, I am equating this random number to that cumulative probability of that particular distribution. And based on that, the random variable can be computed. Fine. Value of the x. So it's basically like if I integrate this between 0 and if I integrate this between 0 and 1.86, this lambda e power minus lambda x, I will get an area or I will get a probability equal to 0.311. So this is like, this is 0, this is 1.86. Which ones? This ones? Yeah, these you are equating them to probability values. See, on a random basis, some numbers are generated for us. Right? On a random basis, some numbers are generated for us. And now, see, this is our cumulative probability distribution curve for any data. It lies between 0 and 1. The shape of it may differ. Right? Now, what we are saying is, on a random basis, let the system generate one number for me. Now that number, I am equating it on this y-axis, which is the probability. So because 0.311 is given, I'll take this as the 0.311. Corresponding to this curve, I will draw one line. And again draw one line here. So this is the value of my random variable. Now if I look at this area under this curve, this would be equal to 0.311. So using 0.311, I am able to generate what would be the random variable associated with the data. So it's like probably, now forget about 1. Probably if I had done 1000 like this, or probably I'll do it on the system more easier for you. Let's say I am generating the same example. First I will generate some 10,000 random numbers or any number. Let's say 1300 random numbers I have generated. You see, they are completely random, right? Now these will follow a uniform distribution, but I want a data which will follow an exponential distribution. This data, when I try to plot now, right, this data when I try to plot now, probably it will give me a kind of a flat. Just to give you that flavor, let me just do that plotting of that. So if I try to plot this graph, almost a flat kind of a graph is there, which is more like your uniform distribution, right? Almost a flat is there, so which is more like your uniform distribution. Now what I require is an exponential distribution. So what I am doing from this data, I am trying to generate an exponential distribution. So from I only have one information about my exponential distribution, that the lambda is 0.2. Nothing else I have. Right? I have nothing else about my exponential distribution. This particular claims follow an exponential, or waiting time follows an exponential distribution with an average waiting time of something. I only have that much information, but now I have to use that information to say what is the chance that the waiting time will be more than some number of hours, right? So what I am doing, I am generating an equivalent exponential distribution value, which is how I am getting, I will equate it to 1 minus e power minus lambda x. 1 minus e power minus lambda x equal to this much, right? So this is becoming, so 1 minus this value is becoming minus, so it is becoming like log 1 minus this value is becoming minus lambda x, right? 1 minus e power minus lambda x equal to 0.7. E power minus lambda x equal to 1 minus 0.7. Minus lambda x equal to logarithm of 1 minus 0.7. X equal to this divided by lambda. So in our case, lambda is 0.2. So minus lambda is minus 0.2. So this is giving me this value. So what is happening in this process? This data will follow an exponential distribution. This data is following a uniform distribution. This data will follow an exponential distribution. Probably let's see how the shape is changing for this. So we are able to convert. So you see it is lying between now 0 and 32. So probably if I try to draw the graph, so this, if you see, is following an exponential kind of a distribution. Earlier it was more of a uniform kind of a distribution. Now it is an exponential kind of a distribution. Now my question could very well go like, okay, if it is following an exponent, let's say the question is, okay, it is following an exponential distribution with a average waiting time of 12 hours, or probably how much, 0.2 days, which is like 4.8 or 5 hours. Average waiting time is around 5 hours. Now tell me, what is the chance that the waiting time will be more than 30 hours? Now I have simulated the data. So there are two values out of probably 1300 or whatever we have generated. There are only two values which are above 30. Now I am clearly saying, so the probability I can compute even through that method. The chance that it will be more without integration, nothing. I did not do anything here. I have simulated the data. So it's as good like I am watching the data. Right? It is as good as I am watching the data. Approximately this will take 6 hours, 1.95. The probably it is like, okay, the first claim has come in 6.1 hours. After that in another 1.95. After that in 0.07. So it's as if you have observed the data and you have collected the data. Right? So if you don't have the information, you can very well generate it using the concept of random numbers, appropriating it to that approximate probability distribution. Same thing you can do in case of discrete distributions also. Like Poisson distribution. He is saying simulate two random values for a Poisson 3 distribution, which means lambda equal to 3 for the Poisson distribution. Using the random numbers 0.812. See, if I am talking about Poisson 3 distribution, what are my values? P of x equal to 0 is e power minus 3 into 3 power 0 by 0 factorial. Right? So what is the, if I try to generate that in Excel, so 0, 0, 1, 2, 3, 4, let's say if I go with this. So Poisson is nothing but e power minus lambda into lambda power x divided by x factorial. Divided by x factorial. So this is around 0.04. Now if I go for this like this, so these are my probabilities. For x equal to 0, the probability is 0.04, x equal to 1, x equal to 2, something like that. Now the cumulative probabilities I will take, because in discrete the cumulative is not a smooth curve, it is like at different points. So I can take the discrete, the cumulative being this plus the previous values. Okay, so it's like this: 0 up to 0, up to 1, up to 2, up to 3, up to 4, up to 5. Right? Now probably you can see the random number is 0.812. 0.812 will come here in the cumulative. Right? Up to 4. So you are simply saying the random variable corresponding to this is nothing but 4. The random variable is taking a value equal to 4 corresponding to the random number 0.812. So if I got a random number 0.812, I'm generating it's like I have generated a value equal to 4. If I'm getting a random number equal to 0.219, generated a random number equal to 2. See, it's as good as, again, if you say I want to talk about the number of claims following a Poisson distribution with an average of 3. Right? Number of claims per day with an average of 3. I want to find out how many such claims are there. I want to model. Okay, first day approximately. So it should, when I want to generate a raw data out of it. I want to generate a raw data out of it, which will give me the same kind of an impact. Once I take all these, so for this 1300 random numbers that are generated, I want to, it's as good as like saying generate 1300 days of claims. Give me the data for 1300 days of claims. I won't have the data, right? What I am saying, because I have the information saying it's a Poisson distribution, I have an information saying the average number of claims is 3 per day. Now generate the reverse for me so that it can help me in modeling the probabilities much effectively. Because I don't need to do complex integrations or any such kind of complexities when I am doing the simulation. I am actually going back and generating the data which will follow a similar kind of a distribution. Now it's like this. By looking at the data, I will have to say whether it follows a Poisson distribution or any distribution. Now what we are saying is, we know it's a Poisson distribution, generate the data. That is the process of simulation. Right? So as far as our exam is concerned, very straightforward. He will give 3 or 4 random numbers. The probable applications of it are extremely higher in any world, because we don't get data. We always simulate the data using the access to the information. So they become very extremely useful. But as far as the exam is concerned, he will give 2 or 3 random numbers like this from that uniform distribution. He asks you to generate some other distribution using this random numbers, using either a discrete distribution or a continuous distribution. But he will ask us to generate those kind of distributions from the random numbers itself. Right?